All right, the continuation of the fundamental theorem of algebra. Typically, if there are 4 or less terms, factoring is going to be the best way to find the roots. If you have more than 4 terms, then factoring can't be used. Also, there are some cases where 4 terms and factoring will not work, so not every equation can you factor it. When factoring doesn't work, then what we can do is we can use the graph to find some real roots, and then use synthetic division to find the remaining roots. And sometimes these are going to be our complex roots, which will occur in pairs. So we have a rational root theorem. It says if the polynomial p of x has integer coefficients, then every rational root polynomial can be set equal to 0 and then written as a factor of a constant and its factor. So example 1 says we have a polynomial equation. It's a 4th degree polynomial and we want to find all of the roots. So since this degree is 4, there's going to be exactly 4 roots. Now these could be real roots, they could be complex roots. So what we do first is we would want to graph this polynomial with our graphing calculator. So if you want to go ahead and pause and enter this into your graphing calculator, it would be y sub 1 equals x to the 4th power minus 3x cubed plus 5x squared minus 27x minus 36. You'd enter that into your graphing calculator. And then you'd want to fit your window so that you can start to see your x-intercepts. And what's going to pop up in your window is something like this. And one of the real roots will be -1 and +4. So these are real roots. So there are 2 remaining roots, and the 2 remaining ones will be complex. So what we do is we use synthetic division . So I'm going to set up my box of my synthetic division. I have a 4th degree polynomial. So I'm putting my placeholders in. And then I'm going to put my coefficients next. So 1, -3, 5, -27, and -36. So now up in our graph, you get to choose if you want to start with -1 or +4. It doesn't matter which one. So I'm just going to choose the -1. So as a factor, it's x plus 1. That's the factor that we're dividing out. And then we do our synthetic division. We bring down the 1. We multiply 1 times -1. And we get -1. We add the column. We get -4. We multiply -4 times -1, which is 4. We add the column. We multiply 9 times -1, -9. We add the column. We multiply. -36 times -1 is +36. And we add the column. At this point, the remainder must be 0. So that remainder is 0. So that's telling us that the root x equals -1 is truly a root of the polynomial. It's a 0. So then what we do is we do synthetic division again with what's left. So you always drop a degree. So this is now my x cubed term, my x squared, my x, my constant, and then my remainder. And I create my next synthetic division box. So I use my remainder, or my quotient from up above with those same places. So you really don't need the are there in our box. Now we're going to work with the second 0. So the second root was 4. So now we do synthetic division with x equals 4. As a factor, it's going to be x minus 4. So now we do our synthetic division. We bring down the 1. We multiply to 4, and we get 4. We add the column. We multiply 0 times 4 is 0. We add the column. We multiply 9 and 4 and get 36. And we add the column. Again, notice that the remainder is 0. It must be 0 for it to be a factor of the polynomial. So now what we did is we divided out the factor x minus 4. So now we drop a degree again. So now this is my x squared, my x, and my constant, and then my remainder. So what we've done is we factored out x plus 1 and x minus 4. Those are our two factors we factored out. What's left is a quadratic of 1x squared plus 0x, which we don't need, and then 9. So those are our factors. Now we move on to solving the quotient. So the quotient is right here, x squared plus 9, to find the remaining roots. So we set that x squared plus 9 equal to 0. We're using our zero product property. And then we solve it. And we subtract 9. We subtract 9. And we get x squared equals negative 9. And then we undo that x squared by square rooting both sides. We get an answer of x equals plus or minus 3i. So we have two roots. They are complex roots. They are complex conjugates of each other. So our 4 roots altogether are negative 1 and positive 4. There were 2 real roots that were x-intercepts. And then our 2 complex roots that are not x-intercepts.